I want to start with some motivation and some ideas of what this overall work is about. So the idea is to have a bunch of robots, possibly heterogeneous ones, so that are sharing the environment, or they need to do some common objective. They need to solve some common task and have some common objective. So one might think, okay, that's just a bunch of robots, and so I can consider them individually. But I mean, what I would like to focus on is rather to consider this group of robots as a system of systems, if we wish. So it's a system composed of multiple entities. And so why could this be interesting? So can we turn off the music, if possible? Yes. Thank you so much. So one of the ideas is that if we have a multitude of robots, so if we have multiple entities, then they could introduce some resilience and to help to deal with uncertainties. Or if we have noise in the system, then we might have a filtering feature given by this multitude of agents. Or maybe if we have some of the agents that are malicious, they are wrong, they are not functioning well, then maybe having multiple of them could help in achieving a better, achieving the objective, let's say. Then another context in which groups of robots, to me, make sense is when you have a task that is spread over a large environment. So if you have a very large environment, maybe a single robot cannot perform well in achieving a task in a decent time or with decent amount of energy and so on. Or the other situation is when you need heterogeneous competencies. So when you have multiple things to be done in order to complete a complex task. So you might either create a super complex individual with many, many competencies, but it could be ineffective, very expensive, difficult to achieve. And so maybe it's better to have multiple elements with different competencies that collaborate. So how can we achieve this? So how can a group of robots achieve a common objective? So in my opinion, the core, the critical point for achieving a common objective is to have coordination among the different entities. So they need to coordinate among each other. And in order to do that, we need to have exchange of information. So different robots need to exchange information among each other. Some kind of information, then of course it depends on the specific task, what kind of information you want to share and what mechanism you want to exploit to exchange such information. So I will start with an example of a recent work that exploits a specific mechanism for exchanging information. And in particular, I would like to start with this example where we have a bunch of very simple robots. It's like actually the kilobot robots, which probably most of you know. They are very simple objects that are very imprecise and they're not reliable per se. The idea is if we mechanically couple them, can we achieve somehow better performances? So then what we did was to actually create this plastic case and plastic springs and use these plastic springs to connect these robots. And actually this study was described in this Nature Communications work. And yeah, so in this work essentially we study how these mechanical couplings can help in achieving coherent motion patterns in very simple and so error-prone individual elements. So in the picture that you see in the bottom, actually, you see these light blue lines. That these are just this is a real picture actually. It's a 7x7 lattice of kilobots, and we just highlighted with the color the springs because they were transparent, so they were the same color as the background. So we just highlighted the springs, but these are the real springs that we used, and we were able to actually to do experiments with this kind of big size interconnection, mechanical interconnection of robots. So what's the point? I will be rather quick. So if you want to have more details, here are the details of the paper, but so the idea is that if you take one single robot, so you don't have any coupling, any mechanical interconnection among the robots, so without the springs, the thing on the left side that you see. And so in this case, this plot show the trajectories of the robots of a repeated experiments. So the robots were supposed to move on a straight line from the left dashed line to the right dashed line. And you can see that they don't really succeed in doing that. So you see chaotic movement because they are really subject to errors. And so we thought, what happens if we connect more of them and see if they physically exchange information among each other in terms of force? Well, one thing that it tried was to interconnect them with rigid links. So in the bottom picture, maybe you don't see it very well, but they are connected with like rigid plastic rods. And so they can exchange information, but they exchange force at the end of the day. But the fact that their links are rigid, well, it changes a little bit the plot themselves, but still we don't really get a good motion from left to right. They definitely don't move on a straight line. We don't manage to move them on a straight line. Actually, it turns out that the presence of elastic links is key in getting a more coherent motion. So, of course, I mean, it's not perfect as you can see in the plot, but still it's much better, it's much more coherent. We can actually somehow define the motion of the system. Also, we managed to actually have an overall shape that can be controllable. So as you see in the right picture, we managed to have this formation that is squeezed and then is expanded. So essentially, putting these elastic links leads to filter out the noise somehow, and so we get coherent motion, an overall shape that is controllable, and essentially this elasticity leads to reduce the effect of the uncertainty that affect the single module, the single elements. Okay, so that was just to start to see how this exchange of information can actually be beneficial in a group of robots. However, I mean, we cannot always think of coupling robots with mechanical links, okay? So very often we will need to have robots that are spread in the environment and they're not close to each other, or we don't want them to be physically connected. And but we still need to exchange information. We still need to have exchange of information to make sure that they can actually collaborate, that they can achieve a common goal. So information needs to be exchanged over a wireless network. So they need to send information to each other somehow, or to get information from the others without physically touching each other. So in this case, anyway, the communication architecture, so the shape of the communication architecture can be modeled as a graph, which I will assume for the time being to be undirected, which means if I talk to you, you talk to me, okay? So, and in order for the exchange of information to be effective, we need to make sure that the graph is connected. So as the robots move, we need to make sure that this graph remains connected. Why couldn't it, why could it happen that it is not the case? Well, it could happen if the communication is based on distance. So let's say that I can communicate to someone only if the distance is sufficiently close. And so if the robots move in the environment, it might be that some connection links break. And so what I'm saying here is that if I want to make sure that robots are able to continuously exchange information among each other, I need to make sure that the communication graph remains connected over time. Well, I can do that essentially in two ways. One is from a local perspective. So essentially by local, I mean that I keep every single link. So I start with a connected network and I make sure that every single link remains connected over time. The other approach that I can follow is that I allow single links to be removed or added as long as the overall graph remains connected, which is much more flexible, right? So, and that's the way that I kind of follow for a few years, yeah? And now I'm showing you, I will just show you one of the most recent works on this topic. I'll just show you a few things about this recent work, which is a paper that was recently published on Automatica. And it follows a line of research where we essentially work on making sure that the graph remains connected, keeping the algebraic connectivity of the Laplacian matrix of the graph larger than 0. Okay? So we have a graph, we compute the Laplacian matrix, the algebraic connectivity is the second smallest eigenvalue of this Laplacian matrix. If you ensure that this algebraic connectivity is larger than 0, then the graph is connected. So how do we do that? In this paper, so we consider robots modeled as single integrators, essentially. And then what we introduce is an approach based on control barrier functions, where we think of having a desired control law, UDES, and you minimize the deviation from this, from such control law. And the constraint that you see in the line below ensures that actually the algebraic connectivity, lambda 2, is larger than a certain threshold epsilon. So if you define epsilon to be larger than 0, so with this method, you make sure that the overall state of the system remains within a set in which the algebraic connectivity is actually larger than epsilon, if epsilon is larger than 0, so you make sure that you have a certain threshold for guaranteeing connectivity. Well, actually, this is actually a simplified version of the thing, because actually there can be problems in the implementation of these things. In particular, the problem that we can have is that the control input that we get from the optimization thing that I showed you in the previous slide could be discontinuous. And actually this can happen when the multiplicity of the eigenvalue of the eigenvalues is larger than 1. So if you have essentially multiple eigenvalues, so lambda 2 is no longer different from lambda 3, for instance. Well, actually, in the Automatica paper that I mentioned, we proposed a method that is based on non-smooth control barrier functions. So it's, I mean, the idea is the one that I showed before, the overall idea, but actually the implementation of the thing is based on non-smooth control barrier function, which is essentially a generalization of control barrier function that ensure, that leads to ensure that the result is continuous. And so we get a better, a more acceptable performance. Well, so now we know how to make sure that information flows among the different robots. And now I want to understand, now I want to highlight this possible issue. What happens if some of the robots are malicious or are broken, or they send wrong information, being it for a fault or for an attack or for whatever? So if you think of a connected network where you have information flowing from one guy to another guy, from one person to another, if you have some wrong information, then this wrong information can drift the overall state of the system to some wrong direction, let's say, and so preventing actually from achieving the objective that you would like to achieve. So this can be a problem, and we need to make sure that in order to have something that can really work in practice, it's important to make sure that we can somehow resist to the presence of malicious agents. Let me say malicious in general, so just to understand. In this recent TRO paper, actually, we study exactly this problem. And so again, using control barrier functions, as you can see in the title. And the idea in this paper is to make sure that the system is resilient to the presence of a certain number of malicious agents. So, of course, you cannot say that you have 100 robots and you have 99 malicious agents, then you cannot do anything, right? But say that you have n robots, then we can show that we can guarantee that if we have up to f malicious agents, then we guarantee that their effect is, I mean, let's say their wrong information has no effect on the overall behavior, or the effect is mitigated. Let's put it this way. So actually, the method starts from this concept that we took from the literature, that if you want to have resilience to f malicious agent, you require the graph, the communication graph, to be 2f plus 1 robust. And I mean, I didn't know what that what that meant, so I assumed that maybe not everybody knows what that means. So I just put a slide to clarify the thing. Actually, so to define R robustness, I need a preliminary definition, which is reachable. So a set. So say that I have a graph where I have nodes and edges, and so I take a set of the nodes, and the set is reachable if we have at least one node in this set which has at least R edges that connect this node to nodes in another set, outside that set. Okay, so we have a sufficient number of connections, let's put it this way. And then a graph is robust if we take every disjoint set of vertices and on all these vertices, this set of vertices are reachable sets, essentially. So at the end of the day, it means that we need to have a sufficient number of edges, a sufficient number of connections. And the idea is like, let's say that I am connected to only one person. If this person is telling me lies, that's the only thing I can know. If I am connected to multiple people, then I have multiple opinions. If one person is telling lies, then I have the other ideas and I can filter out the lie, essentially. So actually, it turns out that this value R is related again to the algebraic connectivity of the graph. And the algebraic connectivity essentially increases as we increase the number of edges. Okay? So given this inequality that we have here, in this paper we introduce a control barrier function that is very similar to the one that I showed before, just ensuring that the algebraic connectivity is larger than this value here. And if we guarantee that, it means that the graph is resilient to F malicious agents, so up to F malicious agents. What's the problem with that? The problem is that this value can be large, can be very big. And so it means that I need to preserve a lot of edges. So I need to make sure that many edges are preserved. So I cannot break edges at the end. So I can have issues like deadlocks as are depicted in this picture. So say that you have robots that need to move from left to right. And so in the left figure, you have robots that encounter a big obstacle. So you would like maybe robots to spread around this obstacle, but to do that, they need to increase the distances and so to break some edges. Or if you have a narrow corridor, in order for them to pass through the corridor, you want them to line up, and so you need to, again, break edges. But maybe you cannot do that because you want to keep resilience. So then now it depends, how important is resilience? So can we accept to lose resilience maybe for a while we pass the corridor, for instance? Well, that's the idea that we are proposing here, is to consider resilience whenever possible as a soft constraint, essentially. So I keep resilience when I can. If I cannot keep resilience, then I simply disregard this constraint. And we achieve this with nested control barrier functions. So very quickly, so we have again something similar to before. So you have a desired control actions and you minimize the deviation from these desired control actions such that you keep the state in a condition where the algebraic connectivity is sufficiently large. And then you take the result of this thing and you guarantee, and you pass this as the desired control action for a connectivity preservation control barrier function. So the idea is essentially that we treat resilience as a soft constraint and connectivity as a hard constraint. So we make sure that we always keep connectivity. And so if everything is working, then we will also keep resilience. If it's not possible, then you can essentially neglect, maybe for a little while, the resilience itself. Then I would like to make a step forward, and let's say that I don't trust anyone and I don't want to communicate with anyone. Okay, I don't trust communication, or maybe I'm not able to communicate because I don't have radio transmission, whatever. So also in this case, it's possible to have exchange of information anyway, and in this case, it will be by means of sensing. So a robot sees or perceives, however, where the other robots are, or what is the state of the other robots in general. About this, we have a RAL paper that is this one that was actually presented by Mattia yesterday in this conference. And in this paper, we consider robots with a limited field of view. So in the picture, you see drones, but it can be any kind of mobile robot. So you have a limited field of view. And so each robot can measure the position of other, or the position, or whatever is the state that you care about. Let's say the position of the others, whenever they are in the field of view. When they are not in its field of view, the robot does not know what's going on. Well, the idea is that if I lose one of my neighbors, I mean, it's not that I completely don't know anything about them. So I just stopped seeing them, but so I can still have a guess of what's their current state. And so we propose essentially a method based on particle filters to estimate the position of the robots that cannot be seen. So here you see that you have these ellipses that collect particles, so that each of these ellipses describes the current estimate of the position of one of the neighbors, of one of the neighboring robots. And the size of the ellipses increases as time goes by. So if I haven't seen you for a while, then maybe I don't know what you're doing. If I have just seen you, then probably my uncertainty is rather small. What's the problem with this approach? One of the problems of this approach is that we need one particle filter for each of the other robots, which means that in particular, if the number of robots increases, we need a lot of particles. And so the complexity becomes very quickly too large to be really feasible, to make the solution meaningful. So what we propose actually is to consider a total budget of particles. So we have a limited number of particles based on the elaboration power that you have available, or whatever, or what you want to use. So you have a total number of, a finite total number of particles, and you dynamically allocate a certain number of particles to the different filters that estimate the state of the different robots. And how can we do that? So, I mean, the idea that we have is to somehow have a notion of relative importance of the other robots, and to have more particles for the robots that are more important. So you have a better estimate of their position. So for instance, let's say that I want to avoid collisions. So whenever it's more likely to have a collision with a certain robot, I will increase the number of particles for the estimator of this specific robot. And yeah, so essentially, I mean, I don't want to say that the things that I showed so far are a solution for all the issues related to this kind of application, but at least I hope that I described a path towards some application of this of groups of robots in this kind of scenario. I just would like to conclude with one of the applications that we have in mind. So, for instance, as I was mentioning at the beginning, one idea is to have is to use multi-robot systems to solve problems that are defined over a very large environment. So for instance, let's say that we want to measure some phenomenon that is spread over the environment. We want to measure or to monitor this phenomenon. Well, we have a recent RAL paper that is exactly about this topic, where we consider a group of robots that are tasked to explore an environment and to detect information about some phenomenon that is defined over the environment, but I mean, without prior knowledge about the phenomenon itself. So the idea that we follow in this paper is to use, we base the methodology on coverage control techniques, and we propose an exploration-exploitation balance. Essentially, what I mean is that by exploration, I mean that the robots are attracted towards areas that are uncertain, so where I don't know what's going on in this area, I don't know anything about the phenomenon in this area. And by exploitation, I mean that robots are attracted towards important areas. So based on the current estimation of the phenomenon that I have just measured, that we as a collective group of robots have just measured, we are attracted towards the most important areas. And the estimation of the phenomenon is based on Gaussian processes. So essentially we define a Gaussian process that that keeps trace of the measurement, that uses the measurement to approximate the phenomenon that needs to be, that is of interest. Well, that's essentially the story that I wanted to tell you. So in this slide, I put a bunch of names of colleagues, collaborators, members of my research group, former member of the research group, co-authors, and if you feel that your name should be there and it's not, then I forgot that. So I will just keep it for just a while so you don't get to actually see if your name is there. And also I'm thanking the funding bodies and the companies that made it possible and are making it possible for me to work on these topics. And with that, I would like to thank you very much, and grazie, arigato